In video number 30 in the Foundations of the Computational Economics course, we will start looking at the problem that will keep us occupied for a number of future videos. This is cake eating problem, which will be transformed into consumption savings model later on. And today we will look at the discrete version of this problem, which is probably, again, the easiest to look at, although compared to the previous discrete models that we've looked at, namely the Zerker bus engine replacement model and the inventory management model. Now, this will present a number of challenges that we want to discuss in this video. All right, so what's the cake eating problem? You have a cake, initially of the size W naught. The question is how much of the cake to eat in each period, and time, as always, is discrete. What is not eaten in the current period t is left for the future. And here we assume that the cake is magical in some sense, that it doesn't get spoiled as time passes. Well, maybe time is very short. Maybe it's just, a minute. So just to recap that every time we're talking about a dynamic model, we have to specify a number of things, namely the choices of the decision maker, which in this case is how much cake to eat, the state space of the problem. Well, let's think on this. It must be, as you remember, the list of variables that are relevant for the choice maker to make the decision in question. The preference of the decision maker has to be specified. So utility of cake consumption in our case, and the discount factor, how the decision maker compares future consumption of the cake to the current consumption of the cake. And then, of course, beliefs of the decision maker, the economic agent. Now, in the problems that we looked at before, for example, in the Rust problem, the state was represented by the mileage, which had random transitions, right? There would be a transition probability matrix, and the state behaved like a Markov chain. In this model, it's much simpler. The cake is just the part which is not eaten is left for the next time period, and so the transition density we don't have to worry about here. But of course, it's conditional on choices, and in this case as well as in all of the previous models, because that's the amount how much we eat today that decides how much is left for tomorrow. Okay, let's assume that the utility of the cake eater is given by a simple log function. That implies a couple of things, right? So, for example, it implies that consuming 0 cake has a minus negative utility. This immediately brings us to the conclusion that the cake will never be eaten completely, which is just a consequence of the utility function here. So it's better not spoil ever. Now, we assume as before that the decision maker is maximizing the discounted expected lifetime utility. Well, expected is a little excessive here. There's no expectation because the cake's transitions are deterministic. We will, again, as before, specify the value function as the maximum attainable value given the size of the cake Wt in period t. And transitions, as we already said, are given by this equation. Well, as I mentioned in the previous videos, transitions don't necessarily have to be physical transitions. These are the beliefs of the decision maker about how the state space evolves conditional on their choices. And so here, this must be a belief, but maybe there's somebody else who is sneaking in the night and eating part of the cake. Okay, so let's write the Bellman equation for the problem as we did before. And here I explicitly start with the maximization problem with the initial cake, W naught. And you can see how this can be separated into two subproblems, or rather the choice in the initial time period can be separated from the choices of all of the rest of the time periods. And look, this part here looks almost the same as this one here, except that the cake became smaller. right? And this is how we can insert the value function, the maximum attainable utility, back into here and get the familiar structure of the Bellman equation with the choice made at this period taking into account the optimal continuation and all of the rest of the periods. This is written for the 0th period, but of course that can be done for any period t, and we get the normal Bellman equation. We note here that there's no expectation because we have a deterministic problem this time, and the law of motion, the transitions are given by simple equation or simple expression here. Okay, so to recap, the state space of the problem is Wt, the size of the cake in period t. Decision variables, there's only one, the size or the amount of cake to eat, Ct, consumption. Instantaneous payoff is given by the utility function, which is log as we assumed. The motion rules are given by the simple recursive expression that say that, you know, the next period size of the cake is just this period minus what we've eaten. And to solve the problem, we need to calculate the value function and the policy function as before. Well, this problem is a lot simpler than the engine replacement model, for example, or even the inventory dynamics model. So let's take a crack at trying to solve it analytically. The standard way to do it in this dynamic models is to make a lucky guess, essentially. Let's assume that the value function, because we know that utility is log, is a linear function of the log of the size of the cake. Okay, if we make this assumption and plug this functional form into the Bellman equation, maybe we can verify that what comes out of the right-hand side of the Bellman equation also has the functional form that fits this linear function of the log, and then we can equate the coefficients. So let's try doing some algebra. Let me first copy this expression that we have. A plus b log w equals max over c of log c plus beta, and I'm plugging in the functional form for the value function again. A plus b log, but this time it's w minus c. Okay, let's try to work with this, and I think I should be able to do a little whiteboard. Right, so let's start with first order conditions for the maximization problem. 1 over c plus what beta b 1 over w minus c minus 1 equals 0, and therefore c times b beta b equals w minus c, and from this it follows that c equals w over 1 plus beta b. We can also calculate right away the w minus c because it enters into the value function, and that's going to be what, beta b1 or plus beta b w, right? Just w minus c. Okay, so now that we know where the right hand side should be maximized, we can plug it in and say that a plus b log w must equal log of c, which is log w minus log 1 plus beta b plus beta a plus beta b log of beta b w over 1 plus beta b. and we take the log of the fraction just as again. Log W, I'm just rewriting first. Minus log 1 minus beta b plus beta a plus beta b log beta b minus beta b log 1 plus beta b, and finally plus beta b log of w. Okay, we have log of w here and here, and so keeping the equation intact, what is it, log w1 plus beta b, and all the rest of the terms are here. I'll just say star. The star stands for all the rest of the terms. Well, now, because this equation must hold for any values of w, then we can equate this b to this coefficient. And this a can be equated to everything which is a constant. And from this, it follows immediately that b equals 1 plus beta b, and that means that b is 1 over 1 minus beta. Oh, it's hard to see. There we are. And in exactly the same way, with more algebra, we can recover a. And here's the answer. A is going to be like this, and b is, of course, that. And plugging this back into our assumptions about the shape of the functions, we finally get that the optimal consumption policy is just a linear function of w. And as you can see, it depends on the beta, the discount factor, which is the preference for patience, essentially. So the higher the beta is for a particular decision maker, the more patient the person is, the more is being left for tomorrow, and the less is being consumed today. But in general, this is a small fraction of the big cake, at any particular cake size w. And in similar way, here's the analytical solution for the value function, which, as we remember, is the maximum attainable discounted utility. This is just a linear transformation of the log, as we assumed. And because it happens to have this functional form, the analytical approach worked. Now, why is this useful? As we can see that in rare occasions that we have analytical solutions, we can check the accuracy of our numerical solution against the analytical one. And this should inform us about the parameters and settings for the numerical methods to solve the models which don't have analytical solutions. Then we proceed as before. We write the Bellman operator. In this particular case, it's very simple indeed. And then we look for the fixed point of the Bellman operator. And as with other problems, the value function iteration solver will work because the Bellman is contraction mapping. Again, we'll talk about the theory of dynamic programming in one of the next videos. So we start with an arbitrary guess for the value function, and then at each iteration we compute the mapped value function by solving the equation, the Bellman equation, the maximization here. And along the way, as an argmax, we will get the optimal policy for the consumption. Okay, and here comes the difficulties that I really wanted to focus on during this in this example. So cake is continuous, and miles process for the bus model, for the bus engine replacement model, miles were also constant. And what we did there was to just discretize, or what John Rust rather did there was to discretize the miles into bins and work with discrete bins, describing the dynamics of the mileage process by a Markov chain defined on these bins. Here, the cake is continuous as well, but moreover, it's not only that the cake is continuous, the decision on consumption of a fraction of the cake means that next period we will have to calculate, or on the next iteration, we will have to calculate the value function at some points which may not necessarily be on the grid. So even we discretize the cake size, and I denote the grid with this vector error on top of W, even if we can discretize the state space as we did in the bus engine replacement model, because the nature of the choice is more complicated, it's not just binary replacement or keeping, we are forced to somehow be able to calculate the value function in the points between the grid. Or at least we have to address this somehow. So, of course, we can and will use interpolation function approximation to do that. But for today, the question is, can we keep it discrete? Can we keep it in the discrete world? So can we cast the cake eating problem as the bus engine replacement problem? And here's a thought. See, conditional on WT, the choice of consumption C defines the WT plus 1, okay? Because WT plus 1 is whatever is left. Now, WT plus 1 will have to be on the grid if we do dynamic programming and keep the state space the same in different time periods. So maybe we could just replace the C with WT plus 1, just swap them, and call the decision variable the next period cake size. This is actually an approach that is sometimes taken in the macroeconomic models, for example. So you could replace the choice variable in such a way that it becomes easier to solve the problem. So imagine that if the next period cake size is actually the decision variable, and consumption is just the difference between WT and WT plus 1, that means that we will never have to calculate the value function off the grid. It's the utility that we may have to calculate for some continuous values of C. But since utility is easy to calculate, it's just a log or whatever other analytical, usually analytical function, then that's not a problem. So here's the plan. We rewrite the Bellman equation in such a way that now the choice variable has to be between 0 and the size of the cake itself, right? And we consume whatever the difference is between the choice, which is the size, how much to leave for the future, and the size of the cake we had now. And then the value function in the Bellman equation that needs to be calculated on the right-hand side is just calculated at the grid point of the future size of the cake. So we note here that the grid is actually used twice. Once it's used here for calculating the value function in each particular iteration, and then it's also used, the same grid is used for the choice variable to be essentially used for the calculation or computing the value of the value function on the right-hand side. So, can you spot a problem? I'll give you 10 seconds to think about that. And there's not going to be any answer right away, but we will arrive at the answer by the end of this video. Let's look at the code instead. And let me go back into the normal notebook mode first. Here, we will use NumPy, of course, and create the class to represent the model just as before. The init method basically just creates the parameters and as attributes of the object. Then this peculiar thing, self epsilon, this comes from the info on the floats for the current machine. Remember, we were talking about the number representations on a computer, and this is the minimum difference between the two floats that we can distinguish. So, well, I call it the smallest positive float number, but it's actually the difference between the float numbers, the smallest difference that we can distinguish. And we will use this as the as a replacement for 0, because we have the log utility function and we don't want to see none, so minus infinities. This is a not a particularly clean approach, but sometimes it's used for its simplicity. Okay, and then we'll create the grid of the problem as the lint space between the small number and the upper bound on the cake size with the given number of grid points. Now, if you remember in the Rust model, we coded up in such a way that changing the size of the upper bound or changing the parameters that the grid depends on would change the grid. Here, we're back to the simplistic approach where the grid is only created at the initialization of the problem object. And that means that we can't really on the fly change the number of grid points or the upper bound of the cake size. We have to reconstruct the whole model. That's all right for our purposes today, though. Okay, let's look at the solver first. It implements the value function iteration algorithm. And as before, we start somewhere. In this case, we're starting at the utility of the cake as if we were eating the whole cake at once. And then it's almost the same as starting from the value of 0. They are different by one iteration, if you think about that. And then for the up to max iter number of iterations, we solve the Bellman equation, right, to get the new approximation for the value function and also the policy function here. We call back if the callback is given, and then we break if the stopping criteria, which is a standard stopping criteria, if that's satisfied. So this is a very same successive approximation solver that we had before. All the complicated details are in Bellman operator. And so here is what's going on. First of all, we take the C to be the current state. The C is going to be the consumption today, but that, as you remember, is the difference between the state today and the choice, which is the same as state tomorrow. So in the tradition of having states in each column of the matrix and choices in each row of the matrix, we convert this one of the grids into a vertical vector, column vector, and take the difference. Namely, we take the difference between the row vector and the column vector to get current states in columns and choices in rows. So these are the consumption levels. Then we do this sneaky replacement of zeros with a small number, again, to avoid the logs of zeros. And here's an important step, which we didn't have before. See, it could be that, you have a small cake now, but you want to also look at the large cake tomorrow, which is impossible in this model, right? You cannot consume a negative amount. And therefore, we want to mask, so to select the points of this C matrix which correspond to positive consumption. And essentially, all the action of the Bellman equation will happen under this selection. All the other points of this matrix C, which is, n grid by n grid, n by n, they will not matter at all because these are the points where the choice is infeasible. It leads to negative consumption. Okay, and then we want to construct the following two objects. So first, this is the matrix of values that we this is the matrix of value function values that we want to output. Okay, so we initialize it with minus infinities. That's what this line does. It just creates a full matrix of n by n and initializes this matrix, all of the elements, to minus infinity. And this V naught is the matrix constructed from the value functions passed to the Bellman equation. So here explicitly, without relying on the broadcasting machinery of NumPy, we want to reshape it into the column vector and repeat it no, wait a second. So current value repeated in columns. So, okay, yeah, so we want to reshape it into a column vector and repeat it so many times to form a matrix with or is it a row vector? Now I'm getting a little bit confused here, just a second. Okay, so V naught is the value function passed to the Bellman equation, and it corresponds to the points in the next period, in the x prime space. And so this reshape, the first reshape, makes a column vector out of past V naught value function. And then this column of different value functions is repeated along the first axis. That's what this one is for. Along the horizontal axis like this. So all of these columns are the same, and they hold V naught. And if you remember, we started with V1 being just the same size matrix of minus infinities. And the C has states and choices. Now, see, the choice in our formulation corresponds to the next period's size of the cake, and therefore the V naught, which is about the next period, the values of V naught are aligned with the choices. So that's how it all makes sense. Okay, and now we can put it all together. The V1 of mask, so we are only working with the points where the consumption is positive. And we can say that they are equal, according to the Bellman equation, the current payoff, which is the log of consumption, plus beta of the V naught. And here we apply the mask as well, because these are the only points that we need from this matrix of the past value function values. Okay, this is the matrix, and now we can apply the Amax operator. So calculate the max over the vertical dimension. So now we've created the states and choices matrix of V1, and now we reduce it along the first axis with the max operator. And that's what happens here, and this creates the one-dimensional array of V1 because of keep dims equals false, so the result will be one-dimensional array. And then we can do a similar thing with argmax. Now argmax returns the indices of the points where the max was attained, and if we look at the grid of those indices, that means that we get the vector of the best possible choices in terms of the next period size of the cake. And then, this difference gives us the consumption. So we will return the consumption, not the optimal policy, but sort of like the optimal policy in the original problem. Okay, that's all for the code. And let's see how it works. Something's wrong. Beta is not defined in model solve. this beta here, so it must be self beta. And here we are. We create the model with these parameters here. Then we solve the model and just print the consumption. Okay, consumption is seems to be pretty much the same until it increases a little bit over here in the end. That's interesting. So how should we analyze these numbers? Well, of course, the best way to do it is to make a plot. And so here in the next cell, we are setting up to make a plot, importing matplotlib. Changing some parameters. This we haven't done before, but in this piece of code, I have implemented that some time ago. Anyway, we create a figure and set up the titles and everything. And then the callback is set up in such a way that it will plot into this created axis. And the axes are defined inside of this function so that the solver can plot into the figure. And let's look what it produces. All right. So it seems that we start with pretty flat value. This is the value function convergence with VFI. A pretty flat value function, which is then sort of becomes more and more concave and then converges, as you can see, to the function over here. Did we converge? So if I say very low number of iterations, then yeah, what is it? No convergence. Oh, so this solver doesn't produce an error. Yeah, it just produced the printout. All right. But you can see how kinky this value function is if we didn't converge, and how smooth it looks if we did in the size of the cake. How many grid points are we using? Are we using here? We're using 50 grid points. I bet. Yeah, in the number of grid points seems to be really important for the answer, and this is the hypothesis that we should check. With 10 grid points, seems that the answer is looking very different now, and it's no convergence, so maybe we need more iterations. Yeah, with more iterations, max iter is just a safety net. We will stop the solver to prevent it to go into an infinite loop for some reason. There could be different reasons, not just the bug in the code. And so with enough iterations, the algorithm did converge, whereas if it doesn't converge for the given number of iterations, well, maybe the safety net is set to strict. Okay, so let's talk about the measurement error. I'll go back into the slide mode. How to measure numerical errors. Since we have the analytical solution, that's where it becomes really, really handy. So we can just compare to this formulas and look at the graph or calculate some deviations. If there is no analytical solution, then it's harder, but it's still possible to often derive some theoretical property of the model or of the solution and just check whether the numerical solution satisfies that theoretical property. But that usually has to be done at a different grid, at a very dense and slow. So this is really a verification of the solution that can be obtained faster. Yeah, we'll look at that later in more details. But for now, we can just compare the value functions. And here we are. Here's our the function lambda, or is a lambda function. This fun is defined as the value function, the theoretical value function of our model. And let's see, this is plotted second, right? Let's make it a color red. There we go. So this is a theoretical value function, and this is the one produced by the model. And they're different quite significantly in the beginning here. What's going on? What about policy function? Here's the theoretical policy function. That's in green. Let's make it red as well. Color equals red. That's what I'm writing here. And you can see that the theoretical, the numerical policy function is definitely not anything like red, although maybe we just don't have enough grid points. So let's make another model. This is a CompEcon grid model. W bar is 10. The number of grid points is 250. We'll solve it, and then we'll plot against the analytical solution. Here we go. What about even more grid points? See, it took some time, actually. It was noticeable. And still, now, what are the steps? Why are we having steps? With 50 points, that's just one step. Why are we having steps? Let me give you some time to ponder on that. All right, well, the steps that we see, this is a direct consequence of our assumption, or of our setup, where we said that the consumption will be equal. This is policy function, right? So this is consumption here. Consumption will be equal the difference between the wealth, where wealth is discretized. So consumption can really move only at a grid that is even smaller than the grid of the value functions. And, it shouldn't be 0 because 0 leads to the negative infinity. But that's probably sort of one step difference between the 2 points of the grid space, of the grid of the cake size. That's probably 2 intervals difference, 3 intervals difference, and so forth. So consumption can only move in these discrete steps, and it can never create a linear function, of course. And, well, I mean, it's sort of linear, and maybe if you increase, you could think that if you increase the number of grid points high enough, then this will become closer and closer. But it is slow. Let's wait. It is slow, and you can see that they seem to converge, but the stepwise the stepwise nature of the computed optimal consumption function, the policy function, never disappears in this approach. So what's the conclusion? Solving this consumption savings problem on the grid does allow us to avoid interpolation and treat the problem completely as if it was a discrete choice, right? Discrete choice similar to the bus engine replacement or the inventory problem. But the cost is the loss of accuracy. There are some further learning resources. You can go to Ada and Cooper book again, and we will be using this book more in the second half of the course. Okay, see you next time.